Okay, so we're going to take off from where we left off last time. So let me remind you, last time we decided we were going to try to study classical gravitational scattering. By classical gravitational scattering, we meant gravitational S matrices whose gravitational S matrices whose singularities were poles which had no singularities other than poles, which were polynomials other than poles. Okay. Now we had a long motivation for this, and at the end of the lecture yesterday, we in last time's lecture we studied all the pole contributions to such. We classified all the pole contributions to such gravitational S matrices, and at the end of last time's lecture, we just began to sort of get into the classification of all polynomial contributions to these S matrices. Okay. The last slide in the last lecture is the one that is up here. In this slide, we try to make precise what mathematical program we were trying to implement. Okay. So what we wanted to do was to classify the most general polynomial S matrix, which mathematically just is the most general polynomial built out of momenta and these polarization vectors. Remember, we had a little discussion about the polarization vectors last time. Such that this expression is Lorentz invariant, separately quadratic in each of the polarizations, where the polarizations are constrained to obey p dot epsilon 0 and also the null polarizations. Okay, invariant under the shift polarization goes to oh, I should fix this. The polarization goes to polarization plus something proportional to the momentum, and also both symmetric, that is invariant under S4 permutations. So this is the mathematical problem we wanted to address, and this is going to take us, at least an hour to complete the addressing this question. Is going to take us at least an hour in today's lecture, possibly a little more. Okay, so this is our program. This is what we're going to try to do. So to start, I'm going to start this this analysis with a little observation. The observation is this. See, what we want to do is just list all polynomials that obey these conditions 1, 2, 3, and 4. But to start with, let's ignore this condition 4. Let's ignore the condition that we need our polynomials to be invariant under the permutations of the 4 gravitons. So we're gonna proceed like this. We're gonna ignore that condition and then later impose it. So we're going to try to solve the mathematical problem imposing just conditions 1, 2, 3, listing all Lorentz invariant polynomials that are separately quadratic in each of the epsilons and so on, invariant under gauge invariance, but ignoring the requirement of permutation invariance. If we do that, we see that this space that we wish to enumerate has a simple and sort of nice mathematical structure. To understand that, that follows from the following obvious and simple observation. Let M be any polynomial S matrix that obeys conditions 1, 2, and 3. So it's not necessarily symmetric under the S4 permutations, but it obeys conditions 1, 2, and 3. Now, if I'm given such an M, then any polynomial, if I take that M and multiply it by any polynomial of ST and U, then it's also an S matrix. It's also an object that obeys conditions 1, 2, 3. Why is that? Condition 1 is that the object has to be Lorentz invariant, but that's okay because S and T are sort of by construction Lorentz invariant. Condition 2 is that it's got to be separately quadratic in polarizations. But since M had the required homogeneity property in polarizations, and S and T are independent of polarizations, condition 2 is not interfered. Condition 3 is that it should be invariant under this gauge transformation separately for each epsilon. But since M was invariant under those gauge transformations and S and T have nothing to do with epsilons, it's obvious that this polynomial of S and T times M also obeys condition 3. Now, this quantity, if M was a symmetrized, was S4, was permutation invariant, the arbitrary polynomial of S and T times M would not be permutation invariant. That's why what I'm saying here works only if we impose conditions 1, 2, 3 by themselves and not condition 4. Okay, but that's the game we're going to play for a while. We're going to impose just 1, 2, 3, not condition 4, and then later impose condition 4. So that's okay. So what we've seen is that the problem of enumeration has a certain structure. If you give me an object that falls within my my class, then I can give you an infinite set of more objects that fall within that class just by multiplying the object you've given me by any polynomial of S and T. Now, you know, this structure, the structure of you give me an object and I give you many more objects by multiplying by a polynomial of some variables, is a structure that is well studied in mathematics. And it has a name. Structures like this are called modules. So what we've just discovered is that the set of objects that obey conditions 1, 2, and 3 are modules over the ring of polynomials of Mandelstam variables. That's the mathematical jargon. I'm now going to explain it. So the next 2 or 3 transparencies are going to be about some elementary structural mathematics, which will prove useful for us as we go. So first, I'm going to remind you about vector spaces. Recall that vector spaces, which we are all, of course, extremely familiar with, are defined, mathematically defined over a field. Now, this field is an object, is some mathematically constructed abstract mathematical space of objects on which you can perform various operations, including addition, subtraction. 2 field elements can be multiplied together, and crucially, 2 field elements can also be divided. Yeah, if I give you field element A and field element B, unless that field element B is exceptional, then we can associate another field element with A divided by B. We don't think too much about this way of thinking about vector spaces normally, because the fields we use usually are the simple ones, either real numbers or complex numbers. Okay. Now, I reminded you of this because a module is very much like a vector space. Instead of being defined over a field, it's defined over what mathematicians like to call a ring. And a ring is a space whose elements can be added together just like a field, can be multiplied with each other just like a field, but cannot be divided. If I give you a ring element A and another ring element B, there is no sense in which I can associate it with it a ring element A divided by B. Okay? So module is like a vector space, except it's defined not over fields, which are like real numbers or complex numbers, but instead over rings, which are objects that can be added and subtracted and multiplied, but not divided. Okay. Now a simple example of a ring is the example we will use through these lectures, which is the space of polynomials of ST and U. You give me a polynomial of ST and U, you give me 2 polynomials of ST and U, I can give you a third one by adding them, or by subtracting them, or by multiplying them. Okay, finite degree polynomials is what I mean. But there is no sense in which you cannot take one polynomial and divide by another and expect to get a polynomial. So division is not an operation within this ring. Okay, so this ring, the space of polynomials of ST and U is going to play the same role, is the ring for this module, and plays the same role that space of complex numbers plays for a vector space. Okay, so we've got these abstract objects, these S matrices, and we've just argued that this space of S matrices is a ring because you give me is a module over the ring of polynomials of ST and U. Because if you give me an S matrix obeying the conditions 1, 2, and 3, I can give you another one by multiplying by any polynomial of ST and U. And ST and U, polynomials of ST and U clearly form a ring. Is this clear? Okay. It's a bunch of terminology for a rather simple notion, but it's useful terminology and will allow us to use it's useful terminology. Okay. Now, a little more about modules. Suppose I have 2 module elements A and B, and they're related by the fact that B is R on A. Okay, so R is a ring element. So in our case, R is some polynomial of S, T, and U. A and B are some S matrices that obey the conditions 1, 2, and 3. Okay? B is an S matrix that is obtained from the S matrix A by multiplying by a polynomial of S, T, and U. In such a situation, I use the following terminology, which I don't think is completely standard for mathematicians, but is very useful and very intuitive for physicists. In such a situation, I say that B is a descendant of the module element A. Okay? So notice that if B is a descendant of A, it does not mean, and in general it's not true, that A is a descendant of B. So being a one guy being a descendant of another is a one-way relationship. Now, most physicists are familiar with one very, for us, well-known example of modules. These are Verma modules for Virasoro, or for the Virasoro group. Okay? In that case, the ring is polynomials of raising operators of L minus n's. Okay? So the polynomials of L minus n's, the role that is played by polynomials of L minus n's in the study of the Virasoro group, of Virasoro modules, is the role that will be played by polynomials of ST and U in the study of S matrices. Okay. Now, we define this notion of a descendant. This is I use the word descendant because that's how we use the word descendant in the case of Virasoro, which we're all familiar. Okay. I define the word descendant. Now, when we study the Virasoro modules, it's very convenient to have the notion of a primary. So let's define that. We say that a module element is a primary of the module, or mathematicians like to call it this generator. Generator is same as primary. A module element is a generator of the module if it is not a descendant of some other module element. Right? If you think about this, exactly how we use the word primary for Virasoro generators. Okay? So now we've defined modules over the ring of polynomials ST and U. We understand what it is to be a descendant, for one module element to be a descendant of another. It means that you've gone from the first to the second, or maybe the second to the first, by acting with the polynomial of ST and U on the second. And we understand what it means to be a primary. Those S matrices that are not descendants of other S matrices. Those S matrices that cannot be built from other S matrices by acting with polynomials of ST and U on them are called primary S matrices. Or is all of this clear? Any questions? Any questions or comments? Great. So I'm going on.
Sorry, Shiraz, I have a question. So in
yes.
general, there will be some bounds on the amplitude at large S and fixed T, right? Typically in theory. So if you allow this module structure, then I mean, if you take amplitude and multiply it with arbitrary polynomial in S and T, then would it
then it will be violated? Yes. So at the moment, the module is just for the set of objects that obey conditions 1, 2, and 3.
So you will put the bounds later.
In 1, 2, and 3, we've imposed no bounds.
Yeah. At
the moment, we're just doing it. You see, the bounds are more tricky because they require physics input. So at the moment, we're just doing kinematical classification. I want to just kinematically classify, solve the classification problem of all S matrices that impose obey conditions 1, 2, 3, and 4, and then later on look at that space and impose other physical constraints.
Okay.
Okay. Great. Fine. Any other questions? Excellent. Now, we define this notion of a generator of the module. Now, the generator of a module the set of generators of a module plays more or less the same role that basis elements play in a vector space. What do I mean by that? When I have a vector space and I give you a basis for that vector space, then any vector in the vector space can be written as a linear combination of the basis elements. In the same way, if I give you the set of all generators, the set of all generators of a module, then any module element can be written as a linear combination of these generators, where the linear combinations, the coefficients of this linear combinations are not complex numbers, but are ring elements. So any S matrix, if I give you the set of all generators, can be written as some polynomial times of ST and U times the first generator, so some polynomial of ST and U times the second generator, and so on. Okay, so I've said this more formally, yeah. I said it formally and forget it. You've got. This is how mathematicians like to say it, and it's how we said it in our paper just to sound cool. But forget it. It's what I said, right? Okay, a set of generators. We've understood what the generators are. Those that are not descendants of anything else. We look at the full set of generators, and once we have the full set of generators, by definition, every other module element is a descendant of one of these generators. Because if it was not, it would be a generator by itself. Okay. Now, module M is said to be finitely generated if it has a finite generator set. That is a generator set with a finite number of elements. All the modules that we will be concerned with are finitely generated. Right. I think this is my last. No, just two more. Just two more slides about this kind of mathematics, and then we get back to back to real life. But just hold on for 2 minutes. There are a few more bits of terminology I need to know. A generator set G is set to generate the module M freely if the following condition holds. The condition is that if I take some linear combination of descendants of the various generators and I get 0, then that cannot happen unless all these Ri's are 0. So that there is no non-trivial descendant of the generator set that vanishes. When this condition holds, the generator set is set to generate the module freely. What does this mean? It means that suppose I take the set of all descendants of the generator G1, set of all descendants of the generator G2, set of all descendants of the generator G3. These descendants are completely, if the module is generated freely, then these descendants are completely independent of each other. There is no way of taking a linear combination of one of this descendant, another of that descendant, another of that descendant, and getting 0. There's no way of writing the descendants of one generator as a linear sum of descendants of other generators. If that happens, if that is the case, then the module is said to be freely generated. Is this clear? Okay, excellent. Now, let me see if I can annotate and draw a diagram. If a module is sort of freely generated, then it has the following structure. This is a primary, and this is the space of all descendants over it. And this is another primary, and space of all descendants over it, and so on. There's a finite number of these primaries, and there's the space of all descendants. And the full module is just a direct sum of these quantities. They're not overlapping. The descendants of this guy, here have nothing to do with the descendants of this guy here, nothing to do with the descendants of this guy.
I have a question.
When the situation happens, the module is said to be freely generated.
Can I ask you a question?
Of course.
So all these S matrix, all the S matrix terms in the Lagrangian should be like are true only up to total derivatives, right?
Absolutely.
So
absolutely.
how do you know one of these polynomials don't act like an integration factor? And
how do I know? Please say it again.
One of these polynomials, once I append the polynomials to the S matrix, they don't act like an integration factor and
I have been inexact here. You see, there was one more condition I should have added here. That is, I'm sorry, I should have added this. These are conditions that obey these up to terms that, up to the equivalences that we only evaluate these polynomials under two conditions. A, sum over pi is equal to 0. And B, pi squared is equal to 0. Okay, we only evaluate these polynomials on shell. Okay, so now suppose I add a total derivative to a Lagrangian, that will not affect these polynomials on shell. So I should have added this. I should have explicitly added this. These two polynomials are equal if they agree with each other when sum over ki is equal to 0 and when pi squared is equal to 0. So we only care about the on-shell and momentum conserving values of these polynomials, because S matrices are only evaluated on shell and only evaluated when momentum conservation is obeyed. So sorry, I should have listed that in this list 1, 2, 3, 4. I should have added 0.5. Yeah, absolutely right. Thank you for. But that's what I meant.
So that implies these factors won't relate them.
Yeah, that implies total derivatives will not contribute, because you see, total derivative has a factor of k1 plus k2 plus k3 plus k4 outside it.
Thanks.
Okay, so you just get 0 when evaluated such that momentum is conserved.
Okay, thank you.
Okay, thank you. Thank you for pointing that out. I should have added one more. I will do that in the slides I submit to the organizers. Thank you for. Okay, any other questions or comments? Great. So you see, a freely generated module is a module where whose structure is like this. Just you've got generators and then descendant towers coming on top of them. Another generator, another descendant tower, and these descendant towers don't talk to each other. A freely generated module is an extremely simple structure. However, many modules in the world are not freely generated. Their structure is more like this. You take the descendants of one guy, take the descendants of another guy, and then there is some overlap. When that happens, you can take the linear combination of this element as obtained as a descendant of this guy, minus this element as the same element as obtained as a descendant of this guy, and that will give you 0. So we've got some descendants, when the module is not freely generated, we've got some descendants of this module that are just vanishing. They're just a 0. These things, when we study Virasoro modules, have a name. They're called null states. Okay, so it's another thing we're very familiar with. Not all modules are freely generated. There are sometimes null states. Okay, and sometimes the null states can be, you don't need 2 different generators. You could sometimes have a module like this, which looks like it should have this element, but actually the linear combination of this element and this element, even for a single generator, vanishes. That would be another null state. Okay. Great. So, okay. So I've tried to explain what I mean by freely generated, non-freely generated modules. Any module that is not freely generated has some linear combinations of descendants being equal to 0. Now, any equation of this form, some linear combination of descendants is 0, is called by mathematicians. I mean, physicists, perhaps you want to call it a null state. Mathematicians like to call it a relation. Now, let's take 2 minutes to study these relations. Let's take 2 minutes to study these relations. Suppose this quantity here, some ring element multiplied by generator I and then summed over various such things. So Rigi is equal to 0. Suppose this turns out to be a relation. Some linear combination of descendants is equal to 0. Now, if that vanishes, then it's clearly also true that I can take this object and multiply it by any polynomial of ST and U, and I'll also get 0, just because this factor was 0. And so we've discovered that the set of relations themselves form a module. Okay? So, a general module can be thought of as the set of Verma modules. That's modules built pretending there are no relations. So that's what a Verma module is. Just act unrestrictedly by all polynomials of ST and U, pretending that there are no relations. So general module is the set of Verma modules of its generators minus the relationship module, the module of relations. But now the relation module itself may or may not be freely generated. Could be freely generated or not freely generated. So then for the relation module, that module is the Verma module of its generators minus the relations for relations. And this structure can go on forever, as actually we're very familiar with in the case of Virasoro. Okay, So this ends my first lightning review of modules and their structure. We've understood various notions. We've understood what a module is. It's something that can be where a bunch of abstract elements where we multiply by ring elements, in our case, polynomials of ST and U, to get new module elements. We've understood that there are special elements in a module called generators. Okay, we can build the whole module by acting with polynomials of ST and U on top of these generators. We've understood that very simple modules are freely generated, so that the set of all polynomials of ST and U acting on these module elements act in an unrestricted manner. These are very simple modules, very easy to enumerate. We've understood that many modules are not freely generated. They have relation modules. The relation modules themselves have to be understood. Okay, any questions or comments about this before we go?
So Shiraz, here all the relations, they come from S plus T plus U equal to 0, or is there something?
No. They can be much more complicated. The main point here is that the momenta that go into forming ST and U also can, those same momenta can dot around with various polarization vectors.
Okay.
Okay. So the index structure coming from the polarizations and the momenta are not separate things. And that is the reason for these relations. S plus T plus U is equal to 0 has already been imposed. Okay. So when I say polynomials of ST and U, what I mean by that is polynomials of the three variables ST and U subject to the condition S plus T plus U.
Okay.
Okay. So that is not considered non-trivial. Okay. Excellent. So let's move on. Fine. So far what I've explained to you is that the set of all S matrices that obey conditions 1, 2, and 3, and also the conditions that the questioner asked me about. You know, two polynomials are distinct only if they differ when sum over ki is equal to 0 and all pi squared is equal to 0. Okay. I should have said that in this list. I didn't. I'm sorry, but that's understood. Okay. We've discovered that the set of the objects that obey these conditions 1, 2, and 3 form a module. But in order to get this nice mathematical structure, we had to completely ignore the fourth and important requirement that we have, namely that our objects should also be invariant under S4 permutations. Now, as I've explained, if I try to impose this invariance under S4 permutations, I'd lose this nice module structure. However, one can impose invariance under a small subgroup of S4 while retaining the S4, while retaining the module structure. And that's what I'm going to explain to you next. Okay. The next thing I want to explain to you is that S4 has a certain interesting Z2 times Z2 subgroup. This Z2 times Z2 subgroup, because it's Z2 times Z2, it has 4 elements. And the 4 elements in question are identity, then the permutation operator that permutes 1 and 2 and 3 and 4, the permutation operator that permutes 1 and 3 and 2 and 4, and the permutation operator that permutes 1 and 4 and 2 and 3. So in other words, the Z2 times Z2 is generated by, well, it consists of identity plus the 3 permutation elements that are just flips in pairs. You can choose your pairs in 3 different ways. 1, 2, 3, 4, 1, 2, and 3, 4, 1, 3, and 2, 4, and 1, 4, and 2. Now, this is, of course, it's a bunch of permutations. It's easy to convince yourself by multiplying any 2 of these elements that you get a 3rd element within this. I mean, that you always stay within this class. So it's a subgroup of the S4 permutation group. What's important about this subgroup is that it is the subgroup of permutations that leaves S, T, and U unchanged. Okay. So, for instance, let's look at how S transforms under the permutation P1, 2, P3, 4. Well, S is just P1 minus of P1 plus P2, the whole thing squared. If I flip 1 and 2 and 3 and 4, but 3 and 4 is playing no role, as I just flip 1 and 2, of course, this doesn't change. So S is left in there. How about T? Suppose I flip 1 and 2, 1 becomes 2. And I flip 3 and 4, 3 becomes 4. So T becomes minus P2 plus P4 the whole thing squared. But by momentum conservation, this is the same as P1 plus P3 the whole thing squared. So T is also embedded. And there's a, though it's gone out of the slide, I'm sorry for that. There's a similar, you can easily verify the same thing for U. U is P1 plus P4 the whole thing squared, which after flips becomes P1 plus P3 the whole thing squared, which is the same as, sorry, P2 plus P3 the whole thing squared, which by momentum conservation is the same as P1 plus P4 the whole thing squared. And then you can verify this for every element of this Z2 times Z2 subgroup. Why is that important? That's important because we now understand that if we didn't impose all of condition 4, but imposed a subpart of that, that is invariance not under all of S4 permutations, but invariance under permutations under Z2 times Z2, then since S, T and U are invariant under these Z2 times Z2 flips, it continues to be true that if I have an element M that obeys my conditions, any polynomial of S, T and U also obeys my conditions. Okay? So imposing not all of S4 invariance, but part of it retains this module structure. We get the set of these Z2 times Z2, but not necessarily S4 times S4 permutation invariant S matrices. We give them a name. We call them the set of quasi invariant S matrices to reflect the fact that they're not completely permutation invariant, but they're not completely non-invariant either. They're invariant under Z2 times Z2. Okay? So the set of all quasi-invariant S matrices, these are not yet physical S matrices, they also form a module. And the rest of these lectures, we will never look at the module of all completely uninvariant S matrices. We'll only study the modules of quasi-invariant S matrices because we can. If we can impose part of the S4 invariance, it's better than imposing none of it. Okay? Great. Now, what we eventually want to do is impose the condition of invariance under all of S4. Now, Z2 times Z2 turns out to be what's called a normal subgroup of S4, which means that if you take S4 and mod it out by Z2 times Z2 action from the right, it's the same as modding it out by Z2 times Z2 action from the left. And both of these ways of modding out S4 by Z2 times Z2 give us another group. And in this case, that group is very simple. It's just S3. So the space of quasi-invariant S matrices are S matrices that, apart from obeying all the other conditions, are also invariant under the Z2 times Z2 subgroup. But they're not invariant under S3. Elements within this module transform in representations of the quote-unquote symmetry group S3. S3, of course, is the permutation of 3 elements. Okay. Now, S3 is a very, very simple permutation group. So it's a permutation group of only 3 elements, and its representation theory is extremely simple. Turns out that the group S3 has exactly 3 irreducible representations. The first one is the completely symmetric representation. Okay, in this representation, every permutation element acts as identity, as one. The second one is the completely antisymmetric representation. In this representation, every permutation element acts like the sign of the permutation. It acts like -1 to the power sign of p, where sign of p is the number of flips you have to use to go from identity to your permutation. These 2 representations, S and A, are both one-dimensional representations. Okay. The third irreducible representation that we call the M representation is the most interesting representation of S3. It's a 2-dimensional representation, and perhaps it's less familiar to you than the others. It's an interesting representation. I won't have time to tell you much more about it. Apart from saying that, if you take the defining representation of S3, the representation in which permutations act on collections of 3 objects, that defining representations obviously can be traded for 3x3 matrices, the action of the permutations on 3 objects. That defining representation is not irreducible, and it can be decomposed into one S and one N. So the M is a part of that defining representation of S3. The defining representation is 3-dimensional. It decomposes into a 1-dimensional S representation and a 2-dimensional M representation. Okay. Our strategy to enumerate all physical S matrices is to first completely enumerate the modules of quasi-invariant S matrices. S matrices that are invariant under Z2 times Z2, but not under S3. Once we've completely understood this module structure, to obtain physical S matrices is simply to take the projection of these modules onto S3 invariants. That part is a very easy step. Okay, the full module can be split up into the part of the module that transforms in the S, the part of the module that transforms in the A, and the part of the module that transforms in the M. And then we just focus our attention on the first part. That gives us space of all physical S matrices. That is the structure we're going to, that is our strategy for how to enumerate these S matrices. Okay, so we've said a lot of things and a lot of it has been irritatingly mathematical. I'm very sorry about that. I'm very sorry about that, but just this turns out to be the most efficient language to express what we wanted to do. So, so I'm sorry about it, but that's how it is. Any questions or comments? We can take questions or comments to clarify this sort of abstract stuff.
Sorry, one question, Shiraz.
Yes.
Is there some physical intuition for why S3 was important? I mean, S4 we can physically argue why we had S4 invariants, but
the intuition is just the following. It is that the space of scattering momenta, the space of Lorentz invariants formed from scattering momenta, transform only under S3, not S4. So, well, I'm not sure this is what you wanted, but let me just say it anyway. You see, under this S3, you see, S4 acts on K1, K2, K3, K4 in sort of like the defining representation of S4. Right? It just permutes these objects one by one. But once you restrict just to Lorentz invariant combinations of K1, K2, K3, K4, and also restrict to Lorentz invariant on-shell and momentum conserving combinations of these guys, this action of S4 is redundant. All elements in the same equivalence class of any one S3 object act the same way on not the momenta themselves, but on Lorentz invariant on-shell equivalent combinations of and momentum conserving combinations of these S4. That's how it comes about. Now, I'm not sure this was intuition. I'm not sure this is okay. I'm not sure I have anything more to say. I agree. It would be nice to say something a little more physical. But okay. Yeah. Sorry. Please follow up if you.
Okay. Yeah. No, I was just wondering if there's some more physical intuition for, like, if you would expect, without going through this module argument, you would expect that S3 would somehow play a role when you defined symmetrized polynomials for the S matrices. But
yeah,
but maybe it's a way.
Yeah, I don't know of. Well, nothing comes to my mind for anything to say apart from what I've said. I would make one more comment. The same structure appears in classifying in counting correlation functions in a conformal field theory. When you count correlation functions in a conformal field theory, once again you find the structure of S3 appearing when you're computing 4-point functions of a CFT, for reasons that are sort of similar to what I just said. But once again, there I don't know of intuition apart from maybe there is something. I don't have anything more to say.
Okay. Hi, Shiraz. So, hi. Can you think of this as like the permutation of 3 particles fixing one of the particles?
Can you think of it as permutations of 3 particles?
Say if I had massive particles in the
Yes.
S frame of one particle and then permuting the other 3 guys.
Yes, 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 yes. That it's. I'm going to interpret your question. You could ask, in every equivalence class, Z. Okay, you could ask the following. Suppose I take an arbitrary S4 permutation. Can I always use Z2 times Z2 to bring it to a permutation in which particle 1 is not moved, but only particles 2, 3, and 4 are permuted? Okay, this is my interpretation of your question.
Yeah,
and with this interpretation, the answer to that question is yes. Yes. So this is one way of trying to see that S4 mod Z2 times Z2 is S3.
So this is some kind of little group, but for choosing one particle.
Some kind of little. Exactly. Yeah, that was well said. Exactly. Let me do some basic counting also, just so that this becomes a little more plausible. Let's remember that S4 has 4 factorial and so 24 elements. S3 has 3 factorial and therefore 6 elements. Z2 times Z2 has 4 elements. And 24 divided by 4 is 6. Excellent.
Shiraz,
more questions? Yes, please.
how does this generalize to higher number of particles?
Yeah, when you go to higher number of particles, typically the set, at least when you go high enough, the set of operations of permutations that leave the Lorentz invariance you can form out of those particles typically becomes trivial. So the role of Z2 times Z2, at least high enough, just becomes identity.
Okay.
So it's quite special to 4.
Okay. Thanks.
Yes. Excellent questions. Please go on. Any other questions about it?
Just one quick question, if I may.
Yes.
Hi. Has parity invariance been imposed anywhere on the amplitudes? Or?
Okay, excellent question, Amin. No, parity invariance has not been imposed in anything that we say. And in fact, in our paper, we have completely worked out all S matrices, both parity invariant as well as parity non-invariant. In these lectures, though, I will largely focus on the parity invariant case when I work out specifics, just to save time. But you look at our paper, you will find every case, including parity non-invariance, non-invariant things being worked out here. So far, nothing I've said has required it to be parity invariant.
And yeah, just one more thing. So this is probably somewhat vague, but I'll ask anyway. So you mentioned about the CFT correlators, like the counting works the same way.
Yeah.
So there for 3-dimensional CFT correlators,
yeah,
there are like some extra relations which make the counting complicated. And so one expects for 4-dimensional amplitude something similar to show up. So
yeah, exactly right. And in fact, we will see the 4-dimension. You know, what we will see is that the modules, the relations that you're talking about, are like the relations for our modules.
I see.
I'm not sure we're talking about exactly the same thing. We will see 2 things.
Yeah.
You might be talking about the number of index structures.
Yeah, I was referring to the fact that when you write in terms of invariants, there are some nonlinear relations between.
Yeah. So you're talking about the index structures. We will see both. So okay. What I'm talking about is. So I withdraw what I said about these module relations. You're talking about something actually simpler. You're talking about the cut down in the number of index structures, basically.
Yes.
And I will show you exactly how that. Hang on for 10 minutes, and if it's not clear, please ask me again.
Okay. Thank you.
Yes. Other questions? Excellent. So let's move on. So, you know, last lecture was full of cool stuff about the invariance of the uniqueness of gravitational scattering amplitudes. This lecture is into grungy, boring mathematics. I'm sorry, that's how life is. And it'll continue to be grungy and boring for the next hour. Then we get back to cool stuff. But please bear with me. Okay. Now, like module elements, you know, all module elements can be decomposed into representations of S3. So the generators of a module also can be, you know, appear in representations of S3. S3 is like a global symmetry of this module structure. Okay. Now, remember that once we had a generator, we had this notion of a Verma module. Like we just act on these generators by arbitrary polynomials of ST and U. And if there happen to be relations in doing that acting, we ignore them. Okay, that's what a Verma module is, just unrestrictedly acting with on a generator by polynomials of ST and U. Okay, what we're going to do now is to count the number of elements in a Verma module. So suppose I give you a generator that transforms in some representation of S3. Luckily, there are only 3 representations. There's the S, there's the A, and there's the M. So we don't have many cases. And then I construct a Verma module built on top of that generator. I want to count the elements in that Verma module. Now, what do I mean by count? Of course, there's an infinite number of elements because I can act with any number of polynomials. But you know, we're used to this in physics, right? Any field theory or any quantum mechanical or most quantum mechanical systems have an infinite number of states. Yet we're able to count these states because we count them. We don't just count the number, we count them graded with respect to some physical quantity of interest. Usually in physical situations, that's the energy, for instance. We're going to do the same thing here. We're going to count the Verma modules graded with respect to 2 things. First, with respect to the dimension, okay, the dimension of the S matrix, and second, with respect to the S3 quantum numbers of the S matrix. Okay, so what do I mean by dimension? Dimension is just derivative number. Okay, so as we assign dimension, I assign dimension 2 to S because it's 2 derivative, 2 to T, 2 to U because they're all 2 derivative. Then the primary itself has some dimension, which you just put in later out. You know, it's just some overall dimension for the whole module. So, okay. So let's start with the primary that transforms in the identity, in the S representation of S3. It's completely symmetric under, it transforms in the trivial representation of S3. It's completely symmetric under all S3. S3 permutation element. Then the Verma module that we get out of it is just this trivial element acted on by all polynomials of ST and U. And therefore, to count this Verma module, graded with respect to S3 permutations as well as with respect to dimension, is just the same thing as counting all polynomials of ST and U, graded with respect to dimension and graded with respect to dimension and S3 representation structure. Okay, so the first question that we are posed with is, can we count the set of all polynomials of ST and U graded with respect to dimension and S3 structure? Now this turns out to be an easy problem. I mean, okay, it turns out to be not too difficult to solve. You can relate it to a problem of counting a set of bosons. I won't. There are cool ways of solving this, cool and rigorous ways of solving this. I'm going to give you the answer and then we'll interpret the answer. And once we've interpreted it, I think you will sort of be happy with this. Okay. The answer turns out to be the following. Let Z alpha X be defined as N alpha N X to the power 2N. Sum over all N. Where N alpha N is the number of representations of type alpha that occur in polynomials of ST and U at degree n. So n is the degree of the polynomial in ST and U. Because each ST and U have dimension 2, we weight things associated with polynomials of degree n with x to the power 2n because we're counting derivative dimension. Now, consider the space of polynomials at a given homogeneity. Let's say polynomials of ST and U at homogeneity n. Separately, homogeneity by homogeneity, these polynomials transform in representations of S3. It's obvious that S3 doesn't mix homogeneities, right? This is just flipping around ST and U. So polynomials of degree n can be decomposed into polynomials of degree n of ST and U. Remember, always imposing S plus T plus U equals 0. Polynomials of degree n of ST and U can always be decomposed into some number of representations that transforms in the S, some number of representations that transforms in the A, some number of representations that transforms in the M representation. So at degree n, let the number of representations that transforms in the S representation be NS n. The number of representations that transforms in the A representations be NA n. And the number of representations that transforms in the M representation is NMN. Okay? Now, once we have these numbers of representations, we make a partition function by summing these over all degrees of the polynomial, but weighted with respect to the dimension. So we get three different partition functions. The partition function over symmetric representations, the partition function over antisymmetric representations, and the partition function over mixed representations. Turns out that these partition functions, which we compute, have a very simple answer. The partition function over symmetric representations is just 1 over 1 minus x to the 4 and 1 minus x to the 6. The antisymmetric guy is x6 times the same guy. And the mixed guy is x squared plus x fourth times the same guy. And now, although we calculate it more seriously, the final answer has a simple physical interpretation. Notice that s squared plus t squared plus u squared is a monomial of st, is a whatever. Is a polynomial of st and u that is manifestly symmetric under S3 permutations. The same is true of st and u. So if you want to make symmetric polynomials of st and u, one way is to make arbitrary polynomials of s squared plus t squared plus u squared and st and u. Interestingly, the serious counting tells us that that's the only way of making symmetric polynomials. That's why this partition function is 1 over 1 minus x to the 4. This factor comes by arbitrary numbers of factors of this s squared plus t squared plus u squared times 1 minus x to the 6. That's arbitrary numbers of powers of this st. Now, these guys can be thought of similarly. You see, if I give you one polynomial that transforms antisymmetrically under permutations, you can multiply it by any number of any polynomial that transforms in the symmetric. And that will continue to transform in the antisymmetric. So the way that it works out is that the set of antisymmetric polynomials is some basic seed antisymmetric polynomials. In fact, in this case, homogeneity 3 or dimension 6 antisymmetric polynomial, whose form we'll write down later in these lectures, times arbitrary polynomials that are symmetric. So that's why this x is 6 times d. And similarly for the m, there are two seed polynomials at degree at homogeneity 1 and homogeneity 2. We'll write these down later in these lectures, multiplied by arbitrary polynomials that are symmetric. So the partition functions over the Verma module restricted to the symmetric part, the antisymmetric part, and the mixed part are very simple, and they're given by this formula. Questions or comments?
Sorry, Shiraz, but got a bit confused. So you can also have like contractions of polarization with momenta, right? In the
you can, but you see, all we're doing here is at the moment we're only enumerating. Enumerating polynomials of st and u. You see, okay. What we're doing, that structure will of course play a key role. But look, all of that is encompassed in this module structure. What we want to do is to build up these modules, and the first object that we build up when we build up these modules are these Verma modules. Take a generator and act with these STs and U's in an unconstrained way.
Yes.
Then there may be relations. You take many generators, there may be relations between one descendant obtained this way and another that we have to deal with. Okay? The analogy here is first we're looking at the Verma modules like for the Virasoro, and then later we will talk about the null states. Okay? So at the moment, building this, please, go on.
Because you said one way to understand S3 is to keep one particle fixed and one particle fixed and one momentum fixed and permute the other three.
Yes.
But then that will have a non-trivial action on the other contractions between epsilons and p's, right? So,
absolutely. So that way of thinking is useful for some purposes. Useful for
okay. Thanks.
Right. Absolutely. Okay. It's not a fantastically useful way of thinking of it, and in our paper we make very little use of it. Yeah. Okay. Excellent. Let's go. So far I've told you about what the Verma module is for the Verma module of a generator, a primary in the symmetric representation. But we also have primaries in either the antisymmetric representation or the mixed representation. Now the Verma module, because it's a Verma module by itself, its nature is with STNU polynomials in an unconstrained way. Okay, it's very simple. You just take the direct product of the generator and the set of all polynomials you get from STNU. Now, when you take the direct product, the generator has some dimension. Let's call it dimension 0. We can add the dimension later on. So in dimension, there's no mixing, but there is mixing in S3 structure, permutation structure. Because now, if we've got some element in the of some polynomial that transforms in some representation of S3, and the generator transforms in another representation of S3, then we get a product representation of S3. So we need to do Clebsch-Gordon to find the actual representation of S3 that we get. What we need are the fusion rules of S3. These are very simple, and I've just written them down. S with anything is that thing, obviously. A with A is S, A with S is A with M is M. M with M, this is the most complicated, is S plus A plus M. Using these fusion rules, we can, and the result here, it is now a simple matter to enumerate the Verma modules of not just representations that transform in the symmetric, but in any representation. In particular, if we're interested not in the whole Verma module, but only the part of the Verma module that is in the singlet representation, it's easy to convince oneself that the restriction of the Verma module to the objects that are in the singlet representation, if we start with the primary that in representation R, is simply ZR as listed here. So for instance, if we start with the primary in the symmetric representation, and then we want to count only elements that are in the symmetric, of course we get ZS by definition. But if we started with the primary in the M representation, and then we wanted to count only singlets, we would have to get only those representations of polynomials such that M times that representation is a singlet. But notice here that in the fusion rules, the M, we only get a singlet in, we don't get a singlet in M times A. We don't get a singlet in M times M, M times S, but we do get a singlet in M times M. So if the primary was an M, we have to count all polynomial representations that were also M, if we want to get those elements that are but themselves singlets. Okay, so fine. So the restrictions of these Verma module, if you've got a primary operator in representation R, and you construct its Verma module, and then restrict that to S3 singlets, the partition function over that is just ZR, which is listed here.
Shiraz, what is interpretation of X square? X4 and X6 you wrote in terms of STU, but Zm has X square also.
This X square?
Yeah,
this
yeah.
X square is the set of linear polynomials ST and U.
Okay, okay.
Okay, consider ST and U. There is no symmetric part of this set of polynomials, because the symmetric guy would be take S plus T plus U, but that's 0.
Okay,
Okay.
yes, yes.
However, so you know, you might think that there were 3 polynomials that were just linear in ST and U. S, T, and U. But because S plus T plus U is 0, there are just 2 of them. And these 2 transform in the M representation.
Okay.
So that's the simplest M representation.
Okay, okay.
Okay, and then multiply that by any symmetric guy, and you get M rep. And
Right.
then the more complicated M representation at degree 2. That we will also, I will list for you later in this.
Okay, thank you.
Okay, excellent. Other questions? Okay, great. So now we have these Verma modules under complete control. Okay, so if we want to completely control the set of all S matrices, now what we need to do is to control we need to A, find the generators of the module of S matrices, and B, find all the relations. These are the 2 things left. Okay, now this is a more difficult job, and in order to implement it, it is useful to have a construction of the module of S matrices as a submodule of a much simpler module, a module that is sort of by definition freely generated, a submodule of a module that we are going to call the bare module through these lectures. Okay, So the next thing I have to do for you is to introduce the bare module and explain various things. So let me start by motivating what I'm going to say. You see, the main difficulty in classifying and enumerating polynomial S matrices is in implementing the gauge invariance condition. The gauge invariance condition by itself reflects the fact that the decomponent vector epsilon mu is actually a highly redundant specification of polarization, because polarization is actually specified by d minus 2 components, as we see from little group analysis. Okay. Yet, in order to have Lorentz invariance, we like to use the full decomponent object epsilon and then remove its two components by demanding that k dot epsilon is 0 and that epsilon goes to epsilon plus k is a redundancy. Okay, so this is the reason for the complication. Now, things would be easier if we somehow went to some sort of light cone gauge, where all our polarization data is manifest, independent, and staring us in the face. And this bare module is the idea that we go to this light cone gauge. So that's what I'm going to explain here. So consider a 4-dimensional scattering process. Sorry, a 4-particle scattering process. Okay? Just like 3-particle scattering processes were associated with a 2-dimensional scattering plane, as we saw in the last lecture. 4-particle scattering processes are associated with a 3-dimensional scattering plane. The set of all the subspace of Minkowski space, that is a linear combination of K1, K2, and K3, and therefore also of K4 because of the momentum combination. Okay, we refer to this subspace of Minkowski space as the scattering 3 plane. Now, every polarization vector that participates in the scattering, just as we did for the two-particle scattering, can be decomposed in the path that's orthogonal to the scattering 3 plane and the path that's in the scattering 3 plane. Just as for just as in the 3-particle case, the scattering 3 plane is a time-like subspace of Minkowski space. The orthogonal space is a space-like subspace of Minkowski space. Okay, now epsilon, the perpendicular part of epsilon, is completely free data. Why is that? You see, epsilon was constrained by 2 conditions. A, that it be orthogonal to, that its dot product with k is 0. And B, that it shifts in epsilon proportional to k are unphysical. But anything that is orthogonal to the scattering plane is orthogonal to all k's and therefore is orthogonal to ki. So the condition that epsilon perpendicular to k is 0 is automatic. Okay, the condition of this dot product being 0 is all a condition on this in-plane part. Similarly for shifts are shifts in this in-plane part. So epsilon I perpendicular is completely free data. Okay, so there are out of the d components of epsilon, d minus 3 lie in this epsilon I perpendicular, and we can specify that completely freely. There's one component left to specify here, and that is more complicated. Why is there only one component? Well, it lay in a 3-dimensional space, but first it had to be orthogonal to its momentum, and secondly, shifts proportional to its momentum are unphysical. So first thing we do is parameterize this epsilon I parallel. Okay, by demanding that epsilon 1 parallel is orthogonal to k1, we can write epsilon 1 parallel as alpha 1 some number times this combination, which is some combination that you can easily verify for yourself is orthogonal to k1 because p1, because if we take p1 dot p2, that becomes like s, and p3 dot p1, that becomes like t, and these two factors cancel each other. Okay, plus an arbitrary shift proportional to p1. This arbitrary shift will have no importance because it's pure gauge, but it also satisfies this shift times dot p1 is equal to 0 because p1 square is 0. And similarly, we can construct the most general form of epsilon 2, epsilon 3, epsilon 4 in-plane parts as shifts proportional p1, p2, p3, p4. These are going to be pure gauge and will have no importance. And then these terms which are important. So all the data in our scattering process actually lies in the d-3 components of epsilon I perpendicular and the numbers alpha for each of the four momenta. So I said that here, AI is pure gauge, but alpha is physical. And you can check that the norm of the vector epsilon I in plane is actually mod of alpha squared. So that's an interpretation of alpha. It's mod squared is the norm of the part of epsilon I that is in plane in the scattering 3 plane. Okay. Now for photons, the pair epsilon I perpendicular and alpha I are completely unconstrained data. These are the d-2 components that completely characterize scattering. For gravitons, we still have to impose a condition that epsilon dot epsilon was 0. That becomes the condition that epsilon perpendicular or epsilon perpendicular plus alpha I squared is equal to 0. You can check that's the case. And so this is not completely unconstrained, but almost unconstrained. And basically, for counting purposes, since every factor of epsilon I dot epsilon I can be replaced by a factor of alpha I squared, we can treat epsilon I dot epsilon I as 0 for counting purposes. It's not really 0, it's epsilon minus alpha I squared. For counting purposes, we can treat it as 0.
Yes.
We can treat it by epsilon I dot epsilon I as traceless dot products. So of course, it makes no sense for them to be traceless because these are Euclidean.
Could you tell again what is this constraint for the graviton? Could you tell again what does the constraint mean for the graviton?
The constraint, you see, you remember that our polarizations for gravitons had to obey an additional condition compared to those for photons. They had to be null polarizations. Epsilon I dot epsilon I had to be 0. This came from the fact that this H here was a traceless symmetric tensor. Okay? So this constraint here is simply the constraint that epsilon I dot epsilon I is 0 written in terms of epsilon perpendicular and epsilon in.
Okay, thank you.
Is this clear?
Yeah, thanks.
Okay, excellent. Okay, so now thought of this way, in this ugly way of thinking. Okay, the S matrix is a function of epsilon I perpendicular and alpha I and S and T separately. Now, this is very important. This is the key point. The key point is that in this way of thinking, there are no dot products between P and epsilon. Why? Because epsilon I perpendicular by definition is orthogonal to all momenta. So it cannot dot with anything. Alpha I, the thing that alpha I multiplies is not orthogonal to momenta. But if I dot a momentum with one of these, what I get is some polynomial of ST and U. So S matrices can be thought of, well, once we think in this language, as like a direct product space. The part that cares about epsilon and alpha, and the part that cares about S and T. These two terms, in this way of thinking, don't talk to each other anymore. Okay, so all the worries that Alok had go away when you parameterize things like this. They're just two different spaces. Okay. Now, something that you can build an S matrix. You can build an S matrix by taking from in this language. You can build an S matrix by taking an arbitrary polynomial of the set alpha I epsilon I that is separately quadratic in each of these sets. So that's two factors of either epsilon 1 perpendicular or alpha 1 perpendicular. So separately quadratic in each of them for each of the particles, and then an arbitrary function of ST and U. This will give you a valid S matrix. Okay, it may or may not be a local S matrix, may or may not be polynomial when written in terms of epsilon and ST and U, but it will be some valid S matrix, and its structure, the structure of these S matrices. S matrices built out of polynomials of epsilon perpendicular and alpha I, and then arbitrary polynomials of ST and U built on top of those. Of course, are a module, and they are what we define to be the the bare module associated with gravitational scattering. Okay, tried to explain to you here is that the bare module is an extremely simple structure. Okay, as an extremely simple structure, its generators are just polynomials of epsilons and alphas alone, and it's a freely generated module. Once I have a generator, I can act on top of it with polynomials of ST and U in a completely unconstrained way, and there's no mixing of any sort. So this is a very simple module of generators. It's freely generated. It doesn't have all the physical properties we want, because we want local polynomials when expressed not in terms of epsilon perpendicular and alpha I, but in terms of epsilon and alpha and P. But it's a very simple module which will prove useful as an intermediate step for us. Any questions about this? Okay, so I've defined for you the bare module. We'll say more about it. Now, before proceeding with analyzing the bare module, just a couple of comments. Suppose I give you an S matrix written as I have done, in some Lorentz invariant, SOD minus 3 invariant expression in terms of these epsilon perpendiculars, alphas, and ST and U, that can always be upgraded to a fully Lorentz invariant S matrix using the following formula. You can show that alphas have a Lorentz and gauge invariant definition like this. You evaluate this, you will find alpha. Similarly, epsilon perpendiculars have a Lorentz and gauge invariant definition like this. We don't have the time to look at these expressions. I just wanted to show you that they existed. Okay, so if you construct something using these epsilon perpendiculars and alphas, you may worry that, okay, maybe this is SOD minus 3 invariant, but not fully Lorentz invariant, but that's not a reasonable, that's not a legit. You don't need to worry about that. You can always turn it into a Lorentz invariant expression using all of these. Okay, and there is a last subtlety that I wanted to tell you about before moving on to analyzing the bare module. That subtlety has to do with the fact that you could ask how pi, epsilon I perpendicular, and alpha I transform under S4 permutations. Pi, of course, transform in the defining representation of S4. Like they just permute around. Same with alpha I perpendicular. Sorry, epsilon I perpendicular. However, these alpha i's turn out to transform more subtly under S4. The reason for that is that alpha I, see, while pi and alpha I, epsilon I perpendicular are characteristics of the particle itself, of the momentum or polarization of the particle itself, alpha i's are particular projections of the in-plane part of epsilon onto momenta of other scattering particles. And when you permute, these projections also get permuted. Okay, this will play no role in my lecture, so I will go very, very quickly through just to alert you that there's a subtlety. Turns out that the action of permutations of these alpha i's is not just that alpha i's transform in the defining representation, transforms in the defining representation time an anomaly factor. This anomaly factor is -1 times the sign of the permutation in question. This plays actually an important role in classifying parity non-invariant S matrices. In this lectures, I will only focus on parity invariant S matrices. It turns out to play no role because every parity non-invariant S matrices turns out to be quadratic in epsilon I perpendiculars and alpha i's for any given particle, and so these -1 to the power sine p factors cancel out in parity non-invariant S matrices. But when you parity invariant S matrices. But when you're analyzing parity non-invariant S matrices, this sort of anomaly under permutations plays an important role. But we want just to alert you to that fact. Forget about it and let's move on. Okay. So I have now defined for you this bare module. The bare module is the set of all Lorentz invariant, Z2 times Z2 invariant polynomials you can form from epsilon I perpendicular alpha I that are separately of degree 2 and epsilon I in the set epsilon I perpendicular alpha I for one I equals 1, 2, 3, 4, and then any number of factors of ST and U. This is an extremely simple structure. Now we come to the really crucial point. In our paper, by doing a set of tedious calculations, we have proved the following. Okay, consider any object that is any S matrix that is of the kind that we are physically interested in. That is an S matrix that is a polynomial in epsilons and ST and U. You know, the full Lorentz invariant epsilons. Such an object is also a polynomial in alpha I, epsilon I, and ST and U. Okay. This is not completely obvious because the relations that relate epsilon perpendicular to epsilon, which sits inside this F, or alpha to epsilon, which sits inside here, have things in the denominator and have strange square roots. So you might think that if I rewrote, you know, some polynomial in the physical epsilons, I could have some strange behaviors when rewriting this in terms of these independent data epsilons. However, that does not happen. We proved this sort of laboriously. Actually, I suspect it's a better proof than the one we have in our paper, but I don't know what it is. So, what I've just explained to you in the language of modules is this. Every physical S matrix, every one of these S matrices that are part of the module of physical S matrices, polynomials of epsilon and P and ST and U, you know, polynomials of epsilons and momenta, any one of those S matrices also belongs to the bare module that we've just defined. Is also a polynomial of ST and U times polynomials of epsilon I perpendicular and alpha I. In other words, the physical module of interest to us is a submodule of the bare module. Okay, so here I've defined this bare module. The bare module is a collection of all Z2 times Z2 invariant polynomials of epsilon I and alpha I and ST, S and T that are separately quadratic in each of these guys. The bare module over the ring of, I've now said in text what I've said to you already in words, that the bare module over the ring of polynomials of ST is very simple. It's generators of polynomials of alpha I and epsilon I perpendicular alpha I, but not of S and T, because of this complete direct product structure once we go to the bare module. Okay, so the generators are just polynomials of these guys that are quadratic in both I in 1, 2, and 3 and 4 variables separately. And we've just argued that the physical module of local S matrices is some module of this bare module. Questions or comments about this?
Sorry, here the third point and the second point, maybe confused. So the second point, you're saying that separately quadratic in epsilon I perpendicular alpha and S and T.
Yes. No, sorry, not separate S and T. Separate
okay.
Each of the sets. This
1,
2, 3, 4.
I see. So they're only built out of epsilon I perpendicular and alpha I.
Alpha I and the quadratic in that set. So you could have a term which is alpha 1 squared.
Yes.
Or a term which has 1 alpha 1 and 1 epsilon 1 perpendicular. Or 2 epsilon 1 perpendiculars. Okay.
Yes.
But it has to have two objects between these two. It has to have two of them. Because it was quadratic in epsilon 1. And epsilon 1 is written in terms of epsilon 1 perpendicular and alpha.
Yes.
Okay, but then it's arbitrary order in ST.
Yes.
Okay, and now the third point is about not the module but the generators. The generators of the bare module are things built not out of any ST and U at all, but just out of the epsilon I's and the alpha I's.
Okay.
Because this bare module is such a simple structure. The floor is very clear. Because the key simplification is that you cannot take a momentum and dot with anything here. Okay, so the complication of the physical module does not exist. Okay,
yes.
So now we have surrounded our problem.
Can I ask a question?
Yes, please.
Yes. So do you think this will be maybe more apparent in the helicity basis or something?
It will be. It's actually helicity basis is very convenient in D equals 4. So in D equals 4, none of this this elaborate structure is needed. There's much simpler ways to work. However, to do it in general dimension gets increasingly arcane in those bases. The advantage of this approach is you do all dimensions in one shot.
Okay.
Yeah. In D equals 4, everything I said could be said much more simply by working with spinor heads. Much more simply. Okay. But the advantage here is that we're looking at all dimensions together. Excellent. Fine. So now what we've done is we've surrounded the problem. You know, the structure of the module of local S matrices was previously completely unknown. Now at least we have a very well understood structure, namely the local module, and we know that the bare module, and we know that our module of S matrices is a submodule of that very well understood structure. So now we have some structure to the problem. There is some submodule inside a module that we understand completely, that we wish to characterize. Okay? So now a problem of characterizing all S matrices is broken up into two parts. First, we have to finish characterizing the bare module. We've almost done it. We have to finish one thing left to do. And the next thing we have to do is then complete the characterization, is to understand what submodule of the bare module physical S matrices. Okay? So now we approach these in steps. Our first aim is to complete the characterization of bare. But before doing that, okay, I'll come back to this.
Sorry, Shiraz, I have one more question. If you
Yes,
look at all polynomials built out of epsilon I perpendicular alpha I,
yes,
because this epsilon and alpha had this strange 1 by s and 1 by square root s, is it obvious you get a polynomial in STN, not some rational?
Yeah, that's the thing. If you built out okay, first, if you build polynomials out of epsilon perpendicular alpha I and then STNU, they will not in general be polynomials of epsilons and STNU. We want to characterize only things that are polynomials in epsilons and STNU. That's why the local S matrix module is not the bare module, but it's a submodule of it.
Okay, I see.
Yeah.
Okay.
And the reason, but there is still a non-trivial thing here, and that is that that local S matrices, when expressed in terms of epsilon and alphas, are indeed polynomials in epsilon and alphas without some, I don't know, square root of S, for instance.
Okay.
That was something that needed a proof, and we proved it.
Okay.
I don't know of an elegant way of saying it, but we proved it. Okay. Yeah. So exactly. So for precisely the reason you mentioned, the bare module is simple, but it's not what we want. However, what we want is a submodule of that. Okay. So now we're going to complete our character. Let me finish this later. I'll come back to this. Let me complete our characterization of the bare module. Okay. We know that the bare module is very simple. It's freely generated. So to completely characterize it, all we need to do is to characterize its generators. Now, to characterize its generators is to do what? Is to count all quadratic polynomials of epsilons and alphas. Okay, is to count all quadratic polynomials of epsilons and alphas that are SOD minus 3 invariant and are also Z2 times Z2 invariant. That gives a complete counting of what you might want to call the index structures of S matrices. I think this is what Amin was talking about in his question. Now, this counting problem, this thing can be done very simply, and I'm going to very briefly outline what we have to do. You see, consider the set of all epsilons and alphas. Okay, the set of all epsilons and alphas such that and look at its representation content under SOD minus 3. What we get is one tensor, that's epsilon with epsilon, one vector, that's epsilon with alpha, and one scalar, which is alpha with alpha. You might have thought that this tensor, actually this is a traceless symmetric tensor. You might have thought, well, what about the trace part of that? Well, remember, epsilon I dot epsilon I for counting purposes can be set to 0 because of the condition epsilon I perpendicular dot epsilon I perpendicular plus alpha I squared is equal to 0. Okay? So in the set of alphas and epsilons, the representation content under SOD minus 3 is a scalar, a vector, and a tensor. So what we want to do is to take this representation content to the fourth power because there are 4 particles. Okay? And then restrict this to Z2 times Z2 invariance and also to SOD minus 3 invariance. We want to count how many such combinations there are. This gives us the set of possible index structures, possible generators of the bare model. Now it's easy, of course, to count SOD minus 3 invariance. It's easy to count Z2 times Z2 invariance. But how do you count both together? There's a sort of cool trick to doing that, which I'm not sure I have the time for. But okay, let me quickly go through. Okay, there's a cool trick using partition functions. Suppose we look at the partition function of this space of indices weighted with respect to Cartan elements of SOD minus 3. Okay. These JMs are Cartan elements of SOD minus 3, and these guys are chemical potentials corresponding to different JMs. And any one of these index structures I'm going to call a one particle state. It's for terminology. So let this partition function over the index structures of one of these particles, the one particle partition function, be Z of Ym, where Ym, remember, are chemical potentials for the Cartans of SOD minus 3. Now consider the Hilbert space of 2 identical bosons of fermions. These bosons of fermions are these index structures, okay? Each of whose single particle Hilbert space is this guy, runs over these I's. So each of whose single particle Hilbert space has partition function Z, Y's. Okay? Let the corresponding Hilbert spaces be denoted by S squared, that means symmetric square of, and lambda squared, which means antisymmetric square of rho. Rho was the single particle Hilbert space of index structures. Now let's compute the trace over this space. So the trace over the symmetrized space is trace over I1, I2, I1, I2, and then you put a projector for this guy to be symmetric. But you know, this is very simple because you see, this projector has 2 terms. There's the half, that just gives us the product of the square of the partition function. And then it has this other part here, which is I1, I2, P12 by 2 times I1, I2. But what P12 does is flip I1 and I2. That's what I've written here. So it takes, that's I1, I2, this business, times I2, I1. So, you know, this inner product is only non-zero if I1 is equal to I2 and I2 is equal to I1. In which case, all charges get doubled because you've got 2 identical particles. And so you get this object here becomes just 1 factor of Z rather than 2 because we're doing a single sum over states times times chemical potential square, because all charges are doubled. So the trace over this symmetrized Hilbert space is Z square of Ym plus Z of Ym square divided by 2. And similarly, the trace of the anti-symmetrized Hilbert space is Z square of Ym minus Z of Ym square divided by 2. Now, what we are interested in is computing this trace not over a 2 particle Hilbert space, but over a 4 particle Hilbert space. If we didn't have the constraints due to Z2 times Z2 invariance, we would just be doing this object. Each trace here would be independent, and so we get Z to the 4 of Ym. But we are imposing the restriction under Z2 times Z2. That is, we're putting this projector, which is 1 plus each of the 3 elements of Z2 times Z2, each of the 3 non-trivial elements of Z2 times Z2 divided by 4 inside this trace. But you see, what these permutations do is flip 1 and 2 and 3 and 4. And so make these objects of I1 and I2 equal to each other in pairs. And so when you work this out, just like in the previous case, you get Z4 of Ym plus 3, that's because of the 3 permutation elements, times Z square of Ym square. Because states were equal in pairs, and there are 2 pairs. That's why Z square, 2 pairs is Z square, Ym square, because states are equal in pairs, divided by 4. And then you can easily check as a matter of algebra that this object is the same as this. So what we've concluded is that the Z2 times Z2 invariant part of the fourth product of a Hilbert of a vector space is the same as the ordinary fourth product of the Hilbert space minus 3 times what you get, fourth product of the Hilbert space minus 3 times what you get by taking the symmetrized product of the Hilbert space, then the anti-symmetrized product of the Hilbert space, and then Clebsch-Gordaning the two. Okay. Now, once you have this, it's very easy to count SOD minus 3 invariants, because what we do is count all the SOD minus 3 invariants that you get by just blindly doing Clebsch-Gordan on four copies of this index space structure, and then subtract what you would get by first symmetrizing, and first anti-symmetrizing, and then Clebsch-Gordan. Subtract 3 times that. Okay. So I went through that a little fast, but we were running out of time. Okay, and using this trick, we can easily count the number of generators in the of the set of Baire modules, both for photons and gravitons. Let's focus on gravitons. We find that for gravitons in d greater than or equal to 8, there are 29 even and none odd. D equals 7, there are 29 even and 7 odd. D equals 6, there are 28 even and 9 odd. D equals 5, there are 22 even and 3 odd. D equals 4, there are 5 even and 2 odd. This reduction from 22.3 to 25.2, this sharp reduction, I think is what Amin was talking about in the reduction in the space of index structures. Okay, now we can do better than just counting the generators. We can also group them into multiplets of S3. I won't explain to you exactly how we did that. I'm just flashing the slide that shows this result. We've got all of these generators decomposed into representations of S3. Okay, so the end result is that this Baire module now is under complete control. We know the space of generators, we know its dimensionality, we know how it decomposes under representations of S3, and then the whole module is just that, the direct product of that with polynomials of ST and U, no complications. Baire module controlled. End of display. Okay, now we turn to the issues of embedding the local physical module inside the Baire module. Any questions or comments before we proceed?
Sorry, Shiraz, the last slide was about the complete classification, all the generators.
All the generators of the Baire module, classified not just by number, but by S3 representation.
Okay.
Okay. Now, I want to make one general comment and then we'll go on to more detail. My time estimate was a little, I'm off on time, but anyway, let's see what it is. The general comment is this one. Where are we? Where are we? Here. Look, next thing that we're going to try to do is to locate the generators of the local module inside the Baire module. Okay. Now, suppose it turns out that there are as many generators of the local module as of the Baire module. This may or may not be the case, but suppose that turns out to be the case. Okay. Then we can ask, is the local module freely generated? Now, if it turns out that there are as many generators of the local module as a Baire module, then of course every generator of the Baire local module, this EJ, this is the notation I'm going to use for the generators of the local module, is some linear combination of generators of the Baire module, where these linear combination are functions of S and T. If the number of Baire module elements and local module elements is the same, then this Pij of S and T is a square matrix. And it's easy to convince oneself, oops, I don't even know where I put it. Then it's easy to convince oneself that, somehow I've lost the transparency, but it's easy to convince oneself that the local module, viewed as a submodule of the Baire module, is itself freely generated if and only if the determinant of this matrix, Pijs of S and T, identically vanishes as a function of S and T. Okay, this is a two-line exercise that's easy to convince oneself. So if it turns out that there are as many generators of the physical module as there were of the Baire module, I've written it in more detail here, yeah. If that turns out, then then only if the determinant of Pij of S and T is 0, is the physical local module not freely generated. If it's not equal to 0, it's freely generated. Now this is a very stringent condition, and it will turn out for us that in 5 and higher dimensions, okay, all the modules we will find, the local modules we will find, will have as many generators in the local module as there were in the bare module, and none of these determinants will ever vanish. So it will turn out that in 5 and higher dimensions, actually the modules, the physical modules, the local submodules of the bare modules will turn out to be actually freely generated, as we prove using this way of thinking. In 4 and 3 dimensions, 3 only makes sense for photons, but 4 makes sense also for gravitons. On the other hand, it will turn out that there will be more generators of the local module than there were of the bare module. In that case, the local module is never freely generated, and then we're left with the task of finding also the relations. Okay, that's all I have to say about general module structure. Now I'm going to take 15 minutes to try to finish our characterization of the local modules, and then take the last 15 minutes to do physics. We're going to have to rush like anything, but questions or comments?
So Shiraz, in the greater than or equal to 5 dimensions, when when these physical modules are freely generated, they're still submodules, of course, of the bare module, right?
They're submodules of the bare modules, but they're submodules that are sparse enough so that wait, how do I annotate? Annotate, draw. There's submodules that are sparse enough so that this thing never happens.
Okay.
So there is a big bare module out here, and they're sparse enough so within this it goes like this. Yeah, this is really made out of many generators, and then they never overlap in their height. In 4 dimensions and higher, however, the picture is somewhat like this. There's submodules and they go like this. This is the bare module. These are the generators, and then there are overlaps.
Okay.
4 and 3 dimensions. Yeah.
Shiraz, just one more thing. If you have a lot to cover, don't rush, because we have. I mean, if you have time, we have a free slot on 30th, so you can take one more lecture. You can go slow.
Oh, okay, great. If you don't mind that,
No. Yeah, please. Yeah. You can take one more lecture on 30th. We will adjust the time with you later, but there is a free slot. So
wonderful. Thank you.
Yeah. Thanks. Yeah.
Okay. Excellent. So then let me go slower. I hope the participants come for that lecture. I assure you that if we have this additional lecture, it will be much more fun than this one, because this is the dry technical stuff which we had to go through to give the whole thing meat. But once we get the meat, that's when we start having the fun. Okay. Okay, excellent. So I'm going to go a little slow. Okay. Fine. Now, the next thing I'm going to try to convince you of, okay, is that we've been doing all this dry mathematics, right? All these modules and modules and modules. Where's the physics? Well, let's bring some physics back into the game. Not really yet. Still kinematic physics, but still physics. So let's start talking about Lagrangians. The first thing I want to explain to you is that the set of all local S matrices are in one-to-one correspondence with the set of local Lagrangians modulo total derivatives and field redefinitions. Okay, set of all local S matrices. You remember what our local S matrices were, right? These polynomials of epsilons and momenta, which obeyed various conditions. I want to convince you that there is a one-to-one map between these guys and local Lagrangians. Now, I'm going to explain that connection to you only in the simplest case of scalars, but it continues to hold also for more complicated situations. But let's try to understand this for the case of scalars. Okay? So suppose we have a theory of a single massless particle. Sorry, I said massless. Let's make it massless. Mass 0. And we look at its Lagrangian. So it's Lagrangian up to a choice of normalization, but we, at quadratic orders always of this form. Well, why is it of this form? Why not more complicated momentum dependence? Because it's of this form because we want to consider theories which have just a single, in their propagator, have a single massless pole. Otherwise, we won't call it a theory of a single massless particle. And that sort of more or less by definition tells us it's of this form, at least if it's local. Now, at quartic order, let's say that this theory has Z2 times Z, has an invariance under Z2, under phi goes to -5. So then at quartic order, this Lagrangian can have much more structure. It can take the following schematic form. It can have various derivatives acting on the 4, 5 fields. And then these various derivatives have indices that can be contracted with each other in various ways. That's just written a very schematic equation. Now, suppose I have this Lagrangian here and I do a field redefinition on it. So the Lagrangian is the sum of this plus this, where this is equal to this, and I do a field redefinition. I make my field redefinition cubic in phi. So the field redefinition is of the schematic form delta phi is equal to B times del phi, del phi, del phi. Now what do I get when I act with this field redefinition on this Lagrangian? Well, the field redefinition, I can have either one factor of delta phi or more factors of delta phi in this field redefinition. So I'm not doing it at linear order, I'm doing it more generally. Okay. If I act on this term with one factor of the delta phi, I will get something that is quartic. If I act on this term with two factors with delta phi both here and here, I will get something that's sextic. If I act on this with even one factor of delta phi, I'll get something sextic. Two factors of the delta phi, I'll get something of degree 8. 3 will degree 10, 4 degree 12, and so on. So you see that this field redefinition generates only one term that is quartic. Okay, every other term that's generated by the field redefinition is of order 6 or higher. Okay, and the term that is quartic is the term that you generate by acting on this guy with one factor of the delta phi. You understand what I mean by one factor of the delta phi, right? You could act, phi has gone to phi plus delta phi, and you keep only one of those two delta phis. But when you do that, I want to know what is the change in the action. Well, what's the change in the action? We get del mu of delta phi times del mu phi, integrate by parts, so that's delta phi times del squared of phi. Okay, and so what we get is that at quartic order we get an explicit factor of del squared of phi times whatever delta phi was, which was this schematic object. So the change in the Lagrangian of the scalar field at quartic order under the field redefinitions I considered is of the form del square phi times anything with 3 phis. Okay. Also, of course, if we added a total derivative to the Lagrangian, we would get del of anything with 4 phis. Now, let's take what I've just said and go to momentum space. In momentum space, the quartic part of the Lagrangian took this form. Okay, so in momentum space, the quartic part of the Lagrangian took this form, and what we see is that under one of these field redefinitions here, okay, what the field redefinition changes this L4, K1, K2, K3, K4 by an object that came from this del square phi and therefore vanishes when K1 squared or K2 squared or K3 squared is 0. So the field redefinition changes this object here. Okay, changes this object here when k1 square or k2 square or k3 square is 0. Sorry, the field redefinition changes this object in a way that changes it when k1 squared, k2 squared, k3 squared are non-zero, but does not change it when all 4 of these guys have ki squared equal to 0. Because it's got this explicit factor of del squared phi here, which translates into one factor of k squared, either for k1 squared or k2 squared or k3 squared or k4 squared. Okay? Similarly, this L here, before we do this integration, this L could have been, it could have been a function of any k1, k2, k3, k4 without imposing momentum conservation. Okay? But we're only interested, the integral over space-time Lagrangians translates into integral of these guys only subject to k1 plus k2 plus k3 plus k4 is equal to 0. That's momentum conservation. And total derivatives change L in a manner that does not change the momentum conserving part of this delta, of this L4 tilde. Okay? So what have we just argued? We've just argued that the space of local Lagrangians modulo total derivatives, okay, and modulo field redefinitions are labeled by this object L4 tilde k1, k2, k3, k4 at values such that ki squared are all 0 and sum over ki is equal to 0. Okay, so there's a one-to-one map. This, what I've done is I've taken the set of all Lagrangians of the scalar field and said that 2 Lagrangians are equivalent to each other if they differ either by a total derivative or by a field redefinition. If I didn't have that original prescription, then Lagrangians would just be labeled by L4 tilde k1, k2, k3, k4, just by this object. But these equivalence classes of Lagrangians are not labeled by this object alone, but instead the part of this object that this function evaluated when all ki squares are 0 and when momentum is conserved. But the part of this object that is evaluated, this object evaluated when all ki squares are 0 and when momentum is conserved is simply the S matrix generated by this Lagrangian for 4 scalar fields. And so we see that there is a one-to-one map, okay, between equivalence classes of Lagrangians, namely local Lagrangians, modulo total derivatives and modulo field redefinitions, and S matrices. 2 Lagrangians that differ by field redefinition generate the same S matrix. 2 Lagrangians that differ by total derivatives generate the same S matrix. So this equivalence class of Lagrangians is labeled by the S matrix. Moreover, this map is sort of invertible. If I give you an S matrix, that's equivalent to me giving you this function L tilde 4, but only for values such that k1 squared, k2 squared, k3 squared, and k4 squared are 0, and such that momentum is conserved. But if I give you such a function, I can just extend this in an arbitrary way. If the function was polynomial, I can extend it in some arbitrary polynomial way to other values of k1 squared, k2 squared, k3 squared, and k4 squared, and values away from momentum conservation. So given any S matrix, in particular given a polynomial S matrix, I can invent some polynomial extension of this away from on-shell and momentum conserving. This extension, of course, will not be unique. But it tells you that there is one Lagrange, given any S matrix, I can associate it with it one Lagrange. Okay? And then this Lagrangian lies in some equivalence class of my Lagrangians. So what I've tried to argue, though I've given you the argument only for the simple case of scalars, is that there is a one-to-one map between equivalence classes of Lagrangians modulo field redefinitions and modulo total derivatives, and S matrices. And if we make it polynomial S matrices and polynomial Lagrangians with total number of derivatives, that goes through sort of unchanged.
Shiraz?
Yes.
So whenever these Lagrangians differ by something proportional to equations of motion,
yes,
can I think of it as some symmetry of the theory with zero Neither-Chats? Like there are these zilch symmetries where because the variation of the Lagrangian goes to 0 on shell, but any variation goes to 0 on shell. So,
well,
I mean, in supergravity, such things appear often. So I was wondering if this was related.
okay, let me think about your question. I normally think of a symmetry as a field redefinition that does not change the form of the Lagrangian.
Yeah.
That the Lagrangian
Right.
old variables has the same functional form as the Lagrangian and new variables.
Mm-hmm. Right.
And that's not happening here.
Right. Right. Only the S matrix doesn't change.
Yeah. So
Right.
I mean, I won't immediately say, maybe there is some sense, but I won't immediately say yes to that.
Okay. Sure. Thanks.
Okay. Okay. Exactly. Okay, good. Now, excellent. Okay. Now, there's, so what we've done is to try to explain that there is a one-to-one map between equivalence classes of Lagrangians and these local S matrices. Okay, local Lagrangians, local S matrices. We're going to use this quite a lot in our classification because for many purposes, it's easier to think of Lagrangians. Well, for some purposes, it's easier to think of Lagrangians than S matrices. Some purposes, it's easier to think of S matrices than Lagrangians. We're going to use this interplay between these two quite often. Okay. Now, when we thought about S matrices, we had this lovely structure for these quasi invariant S matrices. Okay. And that structure was the structure of the module. In particular, given one S matrix, there was a definite sense in which a particular S matrix was a descendant of another S matrix. What is the corresponding statement here for Lagrangians? Okay. The corresponding statement, let me first say it roughly and then I will say it more precisely. The corresponding statement is this. Suppose I give you a Lagrangian with some fields and some number of derivatives. And then I look at another Lagrangian in which I take the first guy, except that I add, let's say, two more derivatives. One of the derivatives acts on one of the fields, the other derivative acts on another field, but then I contract indices. So let me do this with annotate and so that's clear. Okay, so suppose I've got a Lagrangian which is some schematic form. So it's got some field, some other field, some other field, and some other field. These fields could themselves have many derivatives of them. So there could have been a del alpha contracting with some alpha index in this field, and so on. This could be very complicated. But now I take this Lagrangian and act on the first guy with a del mu, and then I act with the second guy also with a del mu. Okay. Now, if I do that, can you see that the S matrix of the associated with the new Lagrangian will be the same as the S matrix associated with the old Lagrangian plus a factor of S square and perhaps T squared and U squared. Why is that? It's because here what we've got is del mu times del mu. In momentum space, del mu times del mu becomes P1 dot P2 in the frame in which this is P1 and this is P2. And P1 dot P2 is simply S squared. There's also a frame in which this is, let's say, P1 and P3, and then that would give, it's not S squared, it's S. Then there's a frame in which this was P1 and P3, and then that would give me T. So you see that the S matrix that I get, if I do such a contraction here, is related to the S matrix of the old object that I got from the old guy by a factor of S or T or U. And that is the notion that we had of descendants. So you see, what I've tried to argue for you here is that within Lagrangians there is a simple notion of descendants. One Lagrangian that is related to another one by having the same structure, except that I've got additional derivatives and that the indices of the derivatives are contracted between each other. Okay, when we have such a structure, the S matrix obtained from the second Lagrangian would be a descendant of the S matrix obtained from the first Lagrangian. Is this clear? Okay. Now, so let me say this a little more precisely. Recall that any set of not necessarily S3 symmetric generators, MA of the local module, is naturally associated with an infinite class of genuine S3 invariant S matrices, S of MA, as follows. These are all the S3 invariant S matrices that are descendants of MA. So I give you a generator of the local module. I have such a generator. Let's imagine that I have such a generator. Now I look at all its descendants. This set of descendants has objects that transform in the S representation of S3, the A representation of S3, and the M representation of S3. If I just restrict attention to those objects that transform in the S representation of S3 alone, those things are actual S matrices, because S matrices are S3 invariant. So associated with any generator MA, there's an infinite set of descendants which are S3 invariant, corresponding to genuine S matrices, even though this generator itself may not correspond to an S matrix, because it may transform, for instance, the M representation. Okay? And then I've said this in mathematical terms. All the S3 invariant generators of S. Now, in a similar manner, any Lagrangian L can be associated with an infinite class of Lagrangians, which I've called C of L, defined as follows. C of L is defined as a set of Lagrangian obtained by taking derivatives on the fields that appear in the Lagrangian and contacting the indices of these derivatives in pairs. And because of what I tried to explain to you, this gives us a notion of when one Lagrangian is descended from another. That is the same notion as when one S matrix is descended from another in the sense of module. Okay, so contracting derivatives in pairs on fields in Lagrangians is the same thing. It plays the same role as contracting indices and as descendants for the S matrix module. Okay, now we say that a Lagrangian L is associated with or corresponds to a generator MA of the set of S matrices if the set of S matrices obtained from the Lagrangians CL coincide with S of MA. That is, we take the Lagrangian, we consider all of its descendants, defined in the way that I tell you about, taking pairs of derivatives and contracting indices. Okay, that gives us a set of S matrices. Lagrangians are therefore a set of S matrices. Now we take the generator MA and consider all its S3 invariant descendants. Okay, that gives us another set of S matrices. If these two sets of S matrices coincide, then we say that this Lagrangian here is associated corresponds to the generator M. This association allows us to use Lagrangians to label generators and more generally elements of the local module. So let me take an example. Consider the photon Lagrangian trace F squared times trace F squared. Trace here just means Lorentz trace. So this means F mu nu, F nu mu. F alpha beta, F beta. Let me write this with annotate. Okay. So trace F squared is F mu nu, F nu mu. That's F alpha beta, F beta, beta alpha. Okay. Now, this object here under this map correspond to generators of the local module of photon S matrices that transform in the tree of S3. This is something I will try to explain in detail as we go down. Okay. Okay. Let me stop this here and explain it in more detail when we come to it. Okay. Now, what do I want to say? What I wanted to say here is the following. I wanted to say that, oops. Sorry, did I leave? Sorry, let me screen share. Can you see my screen?
No, Shiraz. It's,
Okay, sorry. Can you see my screen now?
yeah, maybe you can do full screen. Okay, now it's okay. Yeah.
Okay, excellent. Okay. Right. Okay. In embedding this, in understanding how this, how the space, the module of local Lagrangians or local S matrices is embedded within the space of bare S matrices, we made crucial use of the Lagrangian picture, at least for intuition and often for some of our proofs. Okay. Let me give you a schematic idea of how we used it, and then in the next lecture I will explain. See, the first thing that the Lagrangian picture gives you, using the Lagrangian picture, it's basically clear that there are no local Lagrangians of dimension less than 8. Because all local Lagrangians are polynomials of field strengths, at least in the parity invariant sector. Sometimes you get local Lagrangians using Chern-Simons terms which are less. Well, I'm focusing in these lectures on parity invariant sector. There are no local Lagrangians in dimension less than 8. This tells you that the generators of the bare module, that there are no generators, that there are no elements in the that there are no elements in the local module that have dimension less than 8, and that is that there are no elements in the local module that the bare module starts at dimension, its generators are dimension 0. The fourth order descendants of the bare module have dimensions order 8. Dimensions 8, because that's acting with fourth order polynomial of ST. So the first thing that we see from this point of view is that the first elements of the local module are at least descendant, the lowest elements of the local module are at least of descendant level 4 in the bare module. The descendant level 4 or higher in the bare module. Now, since the earliest generators of the earliest elements, the lowest in derivative number elements of the local module are of descendant level 4 or derivative level 8. So descendant level 4 in the bare module. Anything that is of descendant level 4 in the bare module would be a generator of the local module. Because if it was not a generator, then it would be a descendant of something else. But then it would have to be a descendant of something that appeared at descendant level 3 of the local module, of the bare module. But no such things exist in the descendant level 3 of the bare module. But no such elements exist in the local module. So there's nothing for it to be a descendant of. So any Lagrangian you can write out, all this is saying, it's this fancy way of saying that any Lagrangian that you can write down which is function just of f's and not a derivatives of f's will automatically correspond to generators of the local module. Good. So this is one statement that comes out very easily when you start thinking of Lagrangians. Now there is another statement that comes out very easily. Suppose I have a product of 4 f's, 4 field strengths, and then I take some number of derivatives of these 4 field strengths. Something else that's actually very easy to show is that if the number of derivatives is 6 or more, then all such Lagrangians are descendants of lower level Lagrangians. Okay, so to explain that, let me consider this example. Suppose I take this Lagrangian here, which has 1, 2, 3, 4, 5, and 6 derivatives. I've carefully chosen the indices of these derivatives so as not to contract with each other. See, del A here contracts with this FAB. Del mu here contracts with this mu. B here contracts with this B here, and so on. I've carefully chosen this so that none of the derivatives contract with each other. So you might think, well, okay, this is some term that doesn't look like it's a descendant of something earlier. However, using the Bianchi identity, del A of f mu nu is, this object, we move the indices around so that instead of the A index being a derivative index, if I use this on the first guy, the mu index becomes a derivative index. Once the mu index is a derivative index, this derivative index is contracting with this derivative index. And so that's a descendant of something at 4 derivative order. Similarly, when the nu index becomes a derivative index, that derivative contracts with this derivative. And so the descendant of something at 4 derivative order. Using this kind of idea, you can very easily convince yourself that every term involving 6 or more derivatives of 4 field strengths, if we're trying to construct the local Lagrangian, the local module for photon scattering, every every Lagrangian containing 6 or more derivatives is a descendant of something lower order. So you've already proved now that the sets of generators lie between 8 derivative order, 10 derivative order, and 12 derivative order. 8 derivatives, sorry, dimension 8, dimension 10, and dimension 12. Dimension 8 is stuff built out of just 4 f's. Dimension 8 is stuff built out of 4 f's and 2 derivatives. Dimension 12 is stuff built out of 4 f's and 4 derivatives. Now, if you work harder, you can show that anything built out of 4 f's and 4 derivatives are also descendants of lower order things. So all your generators, just by doing these kind of manipulations, all your generators are things built out of either 4 f's or 4 f's and 2 derivatives. And then by working through the possibilities of all that, you can convince yourself that the set of generators of the local Lagrangians of electromagnetism are trace f squared. This is the dimension 8 guy. Trace f to the 4th. Remember, trace is only in Lorentz indices. There are no non-abelian gauge bosons here. Trace means in Lorentz indices. And this object here. These two are dimension 8, this is dimension 10. Just by doing the kind of manipulations that I described using Bianchi identity, equations of motion, blah, 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 and fooling around, you can prove that every Lagrangian you can write built out of arbitrary numbers of derivatives and 4 f's is a descendant, in the sense that I explained to you, of one of these 3 structures, restricting at the moment to parity invariance. So this Lagrangian manipulations allow us to easily construct the generators of the local module of the set of a local module of electromagnetism scattering. I'll take 2 minutes more and then I'll stop, please.
Okay.
Yeah. Now, once you have these Lagrangians, you can translate this to generators in terms of, epsilons. Okay. The generators I've explicitly listed here, where F1, remember, is P1, F1 mu nu is P1 mu epsilon 1 nu minus P2 minus P1 nu epsilon 1 nu, and so on. So I've given the explicit formula for the generators in S matrix language now, in terms of the epsilons. Now, the bare module structure for the space of 4 photon scattering, if you remember, we counted the generators of the bare module. We can construct the generators of the bare module. And that's given by this expression. Once we have the generators of the physical module, and the generators of the bare module, we can construct how the physical module generators are, in what sense they are descendants of the bare module generators. Oh my God. Sorry. In the last 10 minutes, every time I said dimension 8 for 4 f's, I meant dimension 4. Okay, because f's are derivative, 1 derivative. I'm really sorry about that. And every time I said descendant level 4, I meant descendant level 2. I was confusing myself with gravity, where the role of f is played by r, and that's actually 2 derivatives. So sorry. In the last 10 minutes, I kept saying that things built out of 4 f's are descendant level 4 or dimension level 8. Everything I said that I should rewind and replace that by dimension 4, and descendant level 2. Okay. Sorry about that, please. Sorry for confusion. Okay. And so, okay. And now here what we've done is just very explicitly constructed all the generators of the physical module in terms of generators of the bare module. You see the fact that these quadratic polynomials in STMU tell you that they are level 2 or dimension 4 descendants of the bare module. Now it's easy to count the number of these generators. And there are 7 generators of the bare module and 7 generators of the physical module. So we're in the situation where this Pij object was a square matrix. Now we've explicitly computed this Pij object, so we can compute its determinant. And this is what we find. Some funny number times s to the 5, t to the 5, u to the 5. Okay? And so it is non-zero. This object is non-zero. And therefore, the local module here is freely generated in 5 and higher dimensions. Okay, I should have said that the number of physical module generators was 7 in 5 and higher dimensions. Sorry, the number of physical module generators is always 7. Number of bare module generators is also 7 in 5 or higher dimensions. In 4 dimensions alone, however, the physical module generators have not changed. Nothing changes. The local module generators have not changed. But the number of the bare module generators are now not 7 in number, but 5 in number. That's because in 4 dimensions, let's take 4 as an example. In 4 dimensions, epsilon perpendiculars are now vectors of SO d minus 3, which is vectors of SO1, which means they're just numbers. So these 3 objects, epsilon 1 dot epsilon 2 times epsilon 3 times epsilon 4, which was distinct from epsilon 1 times dot epsilon 3 and epsilon 2 times epsilon 4 when d was 5 or higher, because these were genuine vectors in those dimensions, just become the product of the same 4 numbers in 4 dimensions. So these objects, these bare generators, which were distinct in 5 and higher dimensions, collapse to the same thing in 4 dimensions. So now in this case, while the number of physical generators of the generators of the local module remains 7, the number of generators of the bare module is 5. In this case, the local module is therefore not freely generated. And to completely characterize it, we need to characterize its relations. Okay? This exercise we have completely undertaken. Okay, this is what I've said here. I've listed also the relations. The relations in the physical module turn out to be the objective. Anyway, this exercise we've completely undertaken and thereby completely characterize the parity invariant part of the local module, okay, of scattering for 4 photons, Everything about gravity I've not had the time to tell you about, and since Alok has so kindly offered me an extra lecture, I will tell you about that and the physics in the next lecture. I'm stopping here, but I'll just stop by urging you. I see just from the number of questions that this lecture was both less understandable and less fun than my earlier lecture. I'm sorry about that. You know, there was a certain irreducible technical complexity of the material which I tried to present to you. Okay, that's how it is. The next lecture will have none of these complexities. So do come if you can, and it'll be more fun. Okay.
Yeah, okay, let's unmute our mic and thank Shiraz first. And if there are more questions, we can ask now. So Shiraz, I had a question. So if we take an element which is in the bare module but not in the physical module,
yes.
So it would necessarily correspond to a non-local Lagrangian. Is that
exactly?
Okay.
That would be a Lagrangian that, you know, maybe it's a Lagrangian that could be generated by some loop process or something like that.
Okay.
Yeah, but it's not what we are trying to count. It's not.
Yes. At a classical tree level Lagrangian, it will be non-local.
Yeah, exactly. So yeah. So right, exactly.
Okay. Any other questions?
Shiraz?
Yes.
I have what is possibly a far-fetched question. So, is there any relation what is the relation between this program and, for example, Nima's program of constructing scattering amplitudes as differential forms? I mean, if I know some canonical forms, does it help this program maybe like in the far future? Or?
You see, I know almost nothing about Nima's program beyond what I heard in his lecture he gave to ICTS. So my response to your question is based on what I heard on that lecture. Now, what I heard in that lecture went this way. It went that Nima, what I understood of it, and maybe this is an unfair characterization, and maybe Alok will correct me, but Nima's program is this: that you notice that let's say we focus on tree level. A lot of what he was doing was also focusing on tree level. Let's say we focus on tree level S matrices. We notice that they have certain interesting properties. Right? They cannot have double poles of a certain sort and so on.
Right. Yeah.
Okay. And then so the S matrices from his point of view are some abstract quantities that have some that obey some conditions. And then he tried to find a mathematical construction of a. First, he associated this structure of whatever it's called, something I can't remember what it's called. Some structure that was naturally associated with the lack of funny pole structures, and then he used this differential form to construct not just some structure but actual S matrices that were associated with this polygon structure and obeyed all the consistency conditions. But in the end, what I saw, what he got was the S matrix of one particular theory. Right, this bifundamental theory.
Yeah.
And there was this interesting question about how you could try to generalize it to other theories.
Right.
Okay. This seems, in some sense, almost completely orthogonal to what I'm doing. Because what I'm doing is to write down, also, of course, the great power in what Nima was doing is that he was not restricting to 4 Gravitons. Almost everything he did became...
That was sort of the motivation for my question, in the sense that if we do it for a few points here and somehow there is a description for gravity like that, can we get more hints?
Okay, it's interesting. But one key difference is that the concrete formulas he had, as far as I could tell, were for particular theories.
Right, yeah.
Now, what we are trying to do is explore the space of possible theories.
Right.
So that's sort of different spirit from what he had.
What I was thinking is like if you have like different canonical forms in the positive geometry, probably it would give like different theories.
Exactly right. So I think that you could make contact if you could understand that there was a one-to-one correspondence between his forms, between allowed forms, and Lagrangians modulo field redefinitions.
Right.
That would be then a way of characterizing kinematically allowed S matrices with forms. And then that would become very powerful. Because maybe easier to see forms than what I'm doing. But that step is really needed if you want to connect what he's doing to what I'm doing. Because, a lot of the analysis, at least I got just from his talk, that a lot of the analysis is looking at one example. Not so much as exploring the space of examples.
Right.
But exploring the space is precisely...
They consider the pole structure and factorization structure of a single theory. But yeah, like if you have like different canonical forms, it would probably be different.
Yeah, it would probably be, but you have to make that precise.
Right.
If I understand right, Alok and friends have been looking at this problem to some degree, but it goes beyond just looking at canonical forms, right? Alok, can you should.
Well, actually, I also know very little about the program. We have Song here, so we are only looking at generic scalar interactions. But I think Song can say more about Yang-Mills and gravity maybe for this program.
Sure. Yeah. I think what Shiraz said is in principle, all Shiraz said is correct. That if you want just canonical form of positive geometry, this only give you of scalar theories, because you are not taking into account, say, polarization and so on. You are just working in Mandelstam space, right? So there's a need to first geometrize all this dot product of polarization and momentum. But maybe that's where we can learn from what Shiraz just told. I mean, in the other program. Yeah.
Right.
Okay, thanks.
Thank you.
Sure, just one more question. So there was a question in your previous lecture about BCFW.
Yes.
So would it be correct to say that all the allowed Lagrangians that you're finding for the matrices now at the end, they will all have good BCFW behavior? Is that the can one?
Well, they will not have good BCFW.
Most of them won't have.
Yes, because if they did, they had sufficiently good BCFW, then we would be able to construct 4 particle scattering uniquely from.
Okay, I understand. Yeah, you're ruling them out. You're ruling them out in the end.
Yes.
I see.
You know, BCFW works once you make some assumptions about some high energy behavior.
Right.
What you would basically, the fact that we're finding zillions of examples tells you that BCFW is not working, meaning most of these examples violate your assumption about high energy behavior.
Right.
Okay. Now, most of the next lecture will be about this. It will be about what physical you see, in the program that I've outlined for you, there are 2 parts. There is bookkeeping and there is physics.
Yes.
All of today's lecture was about bookkeeping. All I did was to try to give you a kinematical classification. Okay? Just a kinematical classification of the most general bookkeeping allowed S matrix. Okay? As you saw, that was in itself quite a job. Okay? But once we have the bookkeeping in hand, without making any assumptions about high energy behavior, for instance, which are high energy behavior, I consider physics. Then you need a physical reason to say that some high energy behavior is allowed or not. That's not bookkeeping. Okay. Without making any assumption about high energy physics, I've given you a full classification. Now, some of these may be allowed physically, some of them may not. But now we want to use physics to try to rule them out. I believe that, yeah, right. What would be interesting would be to ask whether the physical constraints that we impose are sufficient. I will give you some bound and related growth, are sufficient to enforce BCFW. That feels like it should be true, but I don't know if anyone's very precise.
I guess the module structure already violates BCFW, right? Because you are allowing arbitrary polynomials of, yeah.
Absolutely. But once we have this module structure, we will then impose some physical constraints.
Yeah.
And then I will, with those physical constraints, find that almost none of these survive. In fact, as you know, I will show that D less than equal to 6. None of these local interaction terms are allowed. None of them, not even one. Okay? So in that sense, in D less than equal to 6, imposing my physical condition, the 4-point function is uniquely determined from the 3-point function because it's just the Einstein 4-point function. Okay? Now, I think it would be interesting, maybe it's obvious, but at least I haven't carefully thought about it. It would be interesting to ask whether that physical condition is also sufficient to ensure that BCFW works. It should then be another proof that if you impose that physical condition, there's a unique Lagrangian. Einstein Lagrangian. Okay, I think that they look like they're closely related because both are about high energy behavior, but I haven't thought carefully about whether one could. It would be nice to prove that. If anyone, if any of the experts have comments, I'd love to.
Song, you have any comment? Yeah, Song is not there. Okay, any other questions?
Hi, Shiraz. I would like to ask you a question about, so on the very first 10 or 15 minutes of your talk last time, in the last lecture, you motivated the fact that you have the vertex operators inserted in the non-compact part of the geometry, the tandem geometry, with no momentum in the compact part, let's say.
Yes.
Now that you have the full classification of the S matrices or the Lagrangians, can we turn on a small amount of momentum in the compact Calabi-Yau or some oscillations of the gravitons in the compact directions and study the deviation of the S matrices away from this universal sector?
Yeah. Now you see, so far, at least in what we've described, so hi Somangshu. So at least in what we've described, as you know, Somangshu, you know, all our objects that are scattering are gravitons.
Right.
Okay. So the moment you start turning on, let's say, momentum in the higher dimensional thing, then what we're doing is not scattering 4-dimensional or p-dimensional gravitons anymore. We're scattering something else, right? Perhaps it would be a massive spin to party. Or if you turn on some excitation, that higher dimensional thing, we're scattering something else. So this classification, the one that I presented, does not immediately help us with what you're suggesting. I see. Yeah. However, what you point out is a very good one. The point you make is a very good one. You know, I'll just repeat something I said last time. I'll tell you how I think it's going to go. I think that somebody is going to prove conjecture 1 or some weakened version of it. So we will have a classification of graviton scattering and its universal extension. You see, remember that in conjecture 1, there was a universal truncation. There was a consistent truncation to the universal sector that included gravitons as well as infinitely many higher spin fields. So somebody will prove this, and then we will have a derivation of this universal truncation, this universal sector, to which we have this consistent truncation. However, that will have no information about the non-universal part, all the fields that were, for instance, the Calabi-Yau excitations. But then what we will do is to start looking at one loop corrections of these classical scattering amplitudes. And then ask what additional fields can we couple to this universal sector, and how can they couple to allow for consistency of the one loop problem. And in doing that, we will discover the internal space. We will discover that the only fields are those that are associated with sigma models and some internal space of central charge 10 minus p, or c hat 10 minus p. That's my fantasy. That's how I think it's going to go. But yeah, it's just a fantasy.
Thanks, Shiraz.
Yeah.
Okay. Are there any other questions? Of course, there's one more lecture, so we can continue after that also.
Shiraz, I'll have one more question. So you made this connection between S matrices and Lagrangians.
Yes.
And to write down S matrix, the most general S matrix, you essentially one of the inputs was gauge invariance.
Yes.
But that's essentially you've imposed a gauge invariance from the Lagrangian perspective, that becomes linearized gauge invariance.
Yes.
So is it true that if I give you any Lagrangian that's invariant under linearized gauge transformations about the Minkowski background, that I can complete it into a full diffeomorphism invariant theory?
Okay. Yeah. Yeah. This is an excellent question, Prab. I don't know if there is a very clear general answer. I mean, surely people believe that it's true.
Yeah.
Right. But I don't know of a clear proof of it. Okay. However, let me make a couple of comments. You see, when does the nonlinear structure start mattering? Suppose we've got something that is order or Riemann to the 4. Your question, of course, is most interesting in gravity, right? For electromagnetism, everything's linear and so on.
Yeah.
No question. Okay, so you said it's a question about gravity. Okay, now suppose we've got something that is like Riemann to the 4. Okay. Mm-hmm. As far as 4 graviton scattering is concerned, Okay, as far as graviton scattering is concerned, the nonlinear structure doesn't matter, because for graviton scattering only gets contributions only from the linear part of each Riemann. Okay, the nonlinear structure would start mattering for 5 and higher order scattering. Right. So now there's a baby version of the same problem. That is, suppose you've got something that is order, let's say, Riemann square. So for instance, the Gauss-Bonnet. Okay, then the nonlinear structure of that starts mattering when we're sorry, let's say Riemann cube. So it's an r to the 6th term, r to the 3rd term. The nonlinear structure of the Riemann there starts mattering when we have when we look at 4 graviton scattering. Now, you see this structure, because we're doing something that has linear plus non-linear, this Riemann cube term will contribute in 2 ways to 4 graviton scattering. First, it will contribute via a pole exchange, where you sow 2 3-point functions through a graviton propagator. Correct. That will be one contribution to 4 graviton scattering. Secondly, it will contribute because you take this Riemann cube and expand it to beyond linear order.
Correct, correct.
Now you want that whole amplitude to be gauge invariant. Okay, the sum of these two things you want to be gauge invariant.
Yeah.
I believe you can prove that that only works provided the whole. You see, it's clear now that 2 things are being linked.
Yeah.
Okay, there is the linear part and the non-linear part that is coming together in the same object.
Yeah.
That same object just has to have invariance under linearized gauge transformations for the external particles. But the internal vertex knows about the nonlinear structure. Okay, and clearly, if the cubic term and the 4th order term were completely unrelated, you'd get a lot of play, and the linearized gauge invariance of the from the external particles would be violated. So I've said this poorly, but let me summarize. I believe that when you start looking at 4-point scattering for a term that starts out at linear order at like H cube, linearized gauge invariance of that 4-point scattering will require a connection between the cubic terms that you put into pole exchange and the quartic term that is just there for contact exchange.
Right.
In fact, in some examples in our paper, we worked this out.
I see, but that should show up in your. Shouldn't that's not relevant for your discussion, because you had these. I mean, your entire talk today was about the contact terms in the S matrix, right?
Yes.
But you also had what you discussed yesterday was the pole part. So isn't there some nonlinear part of the gauge transformation that should relate the contributions to the pole part to these 4?
You see, so today we were only classifying contact terms. So we're only classifying those terms of the Lagrangian that affect 4 graviton scattering but don't affect 3 graviton scattering. Because if it affected 3 graviton scattering, it would not give you just a contact term. It would also give you a pole term. Okay? So to complete the job for gravity, first we're going to have to classify all terms that can affect 3 graviton scattering. But that somebody's already done. And in fact, I will show you how it's done next time. Right?
Sorry, can I just quickly say, so maybe I missed this part. So when you were classifying all of your S matrices from the point of view of polynomials, there's this ring structure.
Yes.
If I just give you a particular ring structure, is it somehow clear that this type of structure can be generated from a Lagrangian perspective by a term that can only contribute to the contact term but cannot contribute to the pole term?
Yes, that's clear. You see, because suppose I take a Lagrangian which contributes also to 3 graviton scattering.
Yes.
Then it would generate the S matrix that you get from that would generate a pole contribution.
Yes.
Right? On the other hand, suppose you take a Lagrangian. So for instance, in the scalar example that I worked out, this toy scalar thing that I worked out, that was built in for me by imposing Z2 invariance. So there was no cubic term in phi.
Mm-hmm. Yeah.
Okay.
Yeah.
But if you take a Lagrangian that has only a quartic term, then there is a one-to-one correspondence between and is local, meaning has a finite order derivative.
Yeah.
Then there is one-to-one correspondence between that and polynomial S matrices. So the structure of this business, the structure of the discussion today for classifying these polynomial S matrices was effectively classifying those Lagrangians that contribute at quartic order but not at cubic order.
Yeah.
Okay, but the Lagrangians that contribute also at cubic order, we independently know. I will review this next time. You get a contribution from Einstein, of course. Then you get a contribution from Gauss-Bonnet and an R-cube term.
Yeah. The 3-point are
the 3-point functions. So the full gravitation S matrix involving exchange of gravitons and other things and nothing else is what you get from Einstein, Gauss-Bonnet, and the R-cube term, plus various local terms. These come basically from Riemann to the 4 terms, up to one exception that I'll tell you.
Yeah. So then, in fact, for instance, if you we should be able to generalize this story to 5-point graviton scattering, right? Because is there any term that contributes only to 5-point scattering but not to 4-point scattering?
Sure. Anything that's built out of 5 powers of Riemann
will
contribute only to 5-point scattering but not 4-point scattering.
Oh, because Riemann is order H. Yes,
right.
Yes.
Actually, anything built out of 5 powers of Riemann plus the third Lovelock term. The third Lovelock term is a term in the Lagrangian term that has only 4 powers of Riemann, but has the funny property that when you expand it in an amplitude expansion in H, starts off at 5th order.
I see.
Some of this I will review. Anyway, yes. So, yes, one could in principle extend this arbitrarily, but it gets more and more complicated to actually do. Okay, to actually prove theorems about it, I think you need some inductions.
Okay, maybe we can stop for today because we have a lecture at 2. Nima's lecture starts at 2. But anyway, I think we will have more time to ask Shiraz after his next lecture on 30th. We will send the exact time later.
Okay, and let me urge you guys again not to be put off by the horribly technical nature of today's lecture. It won't be the same next time. It will be, all the technicalities are done.
Okay, so let's unmute once more and let's thank Shiraz for a fantastic lecture.